computing derivatives. I would like first to recall the definition of the derivative as a limit. The derivative of the function f, denoted by f prime x or by d dx of f, is the limit of f of x plus h minus f of x over h when x approaches 0, if it exists and is finite. Finding the derivative of a function from the definition as a limit is time-consuming and can be very difficult. In this section, we will learn how to use derivatives of basic functions to find derivatives of other functions. Example: if we want to find the derivative of the constant function f(x) equals k, where k is any real number, then you just have to look at the picture, and when you look at the graph of the function y equals k, you see that the slope of this line is 0, and that's why the derivative of a constant is 0. And here is our first derivative of basic function. Derivative of a constant is 0. We are calling this the power rule. For any real number n, the derivative of x to the power of n is n times x to the power of n minus 1. We need to practice that. When you see anything, you just have to figure out what is n. Here definitely n equals 3, so we are going to put this one here. It's like a template, and we will get 3 times x to the power of 3 minus 1, and we get 3x to the power of 2. Here n is 5. We put this in the template, so it's 5 times x to the power of 5 minus 1, which is 5 times x to the power of 4. What is the derivative of 1 over x? We have to write this as x to the power. This is x to the power of negative 1, so n equals negative 1. When n equals negative 1, you can use the template. It's negative 1 times x to the power of negative 1, and we get negative x to the power of negative 2. I'm going to write it in a different way, and I get negative 1 over x to the power of 2. Another example. Differentiate x to the power of 2 over x to the power of 6. We need to simplify this first, because for applying the power rule, we need to get x to a power of something. This is this, which is also x to the power of negative 4. So n here is negative 4. And we will get negative 4 times x to the power of negative 4, negative 1, and we get negative 4 times x to the negative 5, which can also be written as negative 4 over x to the power of 5. This should be familiar. We already calculate this from the definition of the derivative as a limit. Now we're going to do it directly. We just have to figure out what is the power of x. This is x to the negative half. We put this in the template, and we get negative 1/2 times x to the power of negative 1/2 minus 1. We get that. We can write this in a different way. In another example. This looks very complicated, but be careful. You have here a quotient and you have a product, but you don't want to use this fact. What you want to do is to simplify the expression of the x's here to get x to a power of one amount. The power of the x is 2 plus third, because there is a product between those two, minus 1/2 because we are dividing by square root of x, which is x to the power of a half. We do the algebra and we get that the n here is 11/6. When we know that, it is easy. We get that this is 11/6 times x to the power of 11/6 minus 1. So we get this one. The power rules are one of the easiest rules of derivatives. So if you can avoid doing any other rules, but just simplifying first the expression that you are differentiating, you better first do that. Here are more rules of derivatives. If f and g are both differentiable, then the derivative of f plus g equals to the derivative of f plus the derivative of g, or in short, the derivative of the sum is the sum of the derivatives. But also, the derivative of a difference is the difference of the derivatives. And here's the constant rule. For any constant k, the derivative of k times f equals k times the derivative of f. If you pay attention, all these properties are about switching the order of operations. On the left side, you first add the functions or take the difference or multiply by k and then differentiate. On the right side, you first differentiate each one or the function f and then you add, you take the difference or you multiply by k. Example, if you can see, we like now to differentiate the sum of the two functions. So first we are summing up the function, then we differentiate. But the rule, which is the sum rule in this case, allow me first to differentiate each one and then add together the answers. We can now use this rule to differentiate polynomials because we have the power rule, but now we also have the linearity. We know what to do with sum, difference, and multiplication of a constant. And here is the first example. Let's differentiate the polynomial 3x to the power of 2 plus 5x minus 4. First of all, we can use the sum rule and the difference rule to get that. Now we are going to use the constant rule. In the first one, the constant is 3, in the second one, it's 5. Now we know how to differentiate each one of those using the power rule. In the first one, it's 2x, the second one is 1, and d dx of 4, because 4 is a constant, is 0. So we get 3 times 2x plus 5 times 1 minus 0, which is 6x plus 5. Example, d dx of 3x cubed plus 7x over x to the power of 2. Again, we don't have still a quotient rule, but also this is too complicated anyhow. To use the quotient rule in here, we can just distribute the x to the power of 2. We get that. Now we can split it to two derivatives. We can use the constant rule, and we know how to differentiate each one of those using the power rule. From the first one, we get 1, and from the second, we get negative 1x to the negative 2. So altogether, we get 3 times 1 plus 7 times negative 1 x to the power of negative 2, which can be simplified and can be written as 3 plus negative 7 over x to the power of 2, or if you want, 3 minus 7 over x to the power of 2. Let's now learn more derivatives of basic functions. Derivative of exponential function. d dx of e to the x is, surprise, e to the x. And d dx of a to the power of x is ln of a times a to the power of x. And now derivative of logarithmic function. d dx of ln of x is 1 over x, and d dx of log x base a is 1 over x times ln of a. You really just have to memorize that. The explanation are going to come much later when we will do the section of derivatives of inverse functions. Example: differentiate 3e to the x. We are going to use the constant rule, and the derivative of e to the x is e to the x. And we get 3 times e to the x. Now differentiate 7 to the power of x. You just have to memorize that. And here a is 7. And we get ln of 7 times 7 to the power of x. Example: differentiate log x base 3. So because this is the answer, you just have to figure out that a is 3. And you get that. Example: let's differentiate log x base 2 plus 3 times 2 to the x minus 3 to the x plus 5 times ln of x. Because of the sum rule, we just have to differentiate each one of them. Here is for the first one, here is for the second, here is for the third, and here is for the fourth. So you really just have to memorize those. And we will just get that. I'm also was using the constant rule, but now I'm just directly going to differentiate the functions, and I will take the constant rule and the sum and the difference rule as just natural rules to use without any explanation. I would like to put together all the rules of basic functions that we went over today. We went over the derivative of exponential functions, of logarithmic functions, and the power rule. If you add to this the sum, the difference, and the constant rules, you get already a huge bunch of functions that we can differentiate.